So let's welcome our first speaker, Professor Yongsoo Song. And the title of the talk is Accelerating Homomorphic Encryption Operation from Key Decomposition Techniques. Please join me to welcome Yongsoo.
Okay. Good morning, everyone. Thank you for introduction, and it's a great honor being the first speaker of this amazing workshop. And my name is Yongsoo from Seoul National University, and I'm gonna present our very recent work on accelerating nonlinear homomorphic encryption operations. This is quite simple, but in general. And the paper was just set to e-print just a day before yesterday, so you can now see the full paper. And this is a joint work with my dear wife Miran and my PhD student Dongwon and Jinyeong. All right. So my presentation is gonna be a little bit technical, but I'll try to keep as simple as possible. But before that, I should start with some like a background on homomorphic encryption. So historically, after the first FHE came out in 2009, there has been like a significant improvement in various aspects. But I'm more focusing on like algorithmic improvement in scheme designs and optimizations. So the like a VGB scheme was designed in 2012, and like a much improvement was made in 2000 since 2012 to 2006. One example is full RNS FV scheme in 2016, where they designed a variant of FV working on like in the RNS representation without high precision arithmetic. But nowadays, some recent research more like tend to focus on other aspects, like improving functionality of homomorphic encryption or improving usability of HC by designing some compilers, or try to come up with a new hardware optimizing for HC, and so on and so forth. And there are less interest in fundamental HC algorithms, but I was still working on this old school research topic for a while, and there was actually still room for purely algorithmic improvement in HC schemes. So what I have done in this paper was to accelerate what's called the external product. So this external product is an operation key building block of literally all nonlinear homomorphic encryption operations of various schemes. Especially it is used in what's called the key switching, and key switching is again used in homomorphic multiplication or automorphisms of VGB, FV, and CKK scheme, and also a similar operation is used in GSW-like operations. So advantage of an implication of this work is as follows. So we could achieve better performance in terms of both asymptotic and concrete complexity. And then this is compatible with the prior method. So you don't have to choose one of these old or new method, but you can just implement both method and choose whatever you want to use. And I'll show you later, but I believe this research may change some future directions on hardware accelerator research. Okay, so in this talk, N is gonna be ring dimension, which is a power to integer, and R is a ring of integers. R sub Q is a R mod Q raised to Q, and here ciphertext modulus Q is a product of Q1 to QL. Let's say Q1, Q2, QL are like a distinct word size primes. Okay, so some boring part. So in many HC schemes, we use this RNS and entity. RNS stands for register number system. So when you set this ciphertext modulus as a product of distinct primes, you can actually use this ring isomorphism from Chinese remainder theorem. So if A is an element of a ring modulo Q, then instead of using this multi-arithmetic, multi-precision representation, you can represent A as a tuple of A modulo Qi, and each A mod Qi is word size. And for arithmetic operation, you can just add or multiply in this RNS space. We often, we informally say that a function is RNS friendly when the function can be evaluated in the RNS form without going to multi-precision representation. And inside of each R sub mode Qi, we again use number theoretic transformation. That's a special FFT over finite field. So if Qi is a 1 modulo 2n, then there is a trans-primitive root of unity. So we can use, again, another layer of isomorphism from R sub Q to tuple of Z modulo Q, defined by this evaluation of a polynomial at roots of unity. So this is a ring isomorphism again. So there are two types of polynomial representation for A. The first one is a coefficient form. So you can simply consider the tuple of its coefficients. And another is called the entity form, where you store these evaluation values. So entity form is more suitable for arithmetic operation, while coefficient form is necessary when you evaluate some like a non-arithmetic operation like a Gaussian decomposition, which I will explain in the next slide. So Gaussian decomposition. So I'm gonna, this is a very simplified version of a Gaussian decomposition explanation. So we usually often use this technique to reduce the noise growth. So Gaussian vector is a fixed vector in modulo Q. And let me denote by this inner product function by simply G. So G is an inner product function which takes a k-dimensional vector as an input and output this inner product. This product is well defined because this RQ is an R module, and Gaussian decomposition is, roughly speaking, is a process to find a short preimage of this inner product value. So in other words, A is an input in RQ, and decomposition of A is a k-dimensional vector B1 to Bk, such that this linear combination of Gi is equal to A modulo Q. So roughly speaking, this G1 to Gk, they are fixed bases, Gaussian bases, and you can actually represent an arbitrary element of RQ as a linear combination of these GIs with a very small coefficients. So this is a transform from like a ring, residue ring to small ring, normed space. Here's one example. So if we have this RNS basis, and then you can consider what's called the prime decomposition, where H of A is defined simply as a tuple of A modulo Qi. It looks very similar to RNS representation of A, but actually they are different because RNS representation was introduced to like make algebraic isomorphism between RQ and product of RQi. But these elements that I have written as A mod Qi, they are elements of R with some size. So algorithmically, they are just different stuff. So this decomposition is actually a valid Gaussian decomposition corresponding to Gaussian vector. This Gaussian vector is just a CRT constant, and you can check this correctness. So now, let me quickly explain why this Gaussian decomposition or other stuff are so important in HE design. So now I will define so-called external product. So the same terminology is used to often refer the product between ring LW ciphertext and ring GSW ciphertext, but I am here's a more like a general definition of external product. So now we have one input A. A is often a ciphertext component in RQ, and U is usually some like a vector of polynomials mod Q, U is usually often part of some evaluation key. It can be a linearization key or automorphism key. And external product first decompose this ciphertext entry into this vector of small polynomials and take a linear combination of UI. This is called the external product. So from the definition of a quadratic decomposition, if you take a external product between any polynomial A and a quadratic vector G, then you recover the original A. And when U is like a pair of two vectors U0, U1, then I will denote this two external product by simply using the same notation. Okay, so this is finally the slide explaining why we are so interested in this quadratic decomposition stuff. So in CK case, for example, when you multiply two ciphertexts, you have two pair of polynomials, and if you simply multiply them, you obtain a triple of polynomials, which can be decrypted by 1s and s square. So this s square term is problematic. So you need to be able to somehow transform this entry into the standard Ring-LW ciphertext, which can be decrypted by just original S. So that's where the key switching key comes into. So in general, a key switching key from S prime to S can be written as this form, where this part is simply a stack of many Ring-LW encryption. So encryption of 0, you can say. And here's a message S prime times the Gauge vector. So if you, for any ciphertext component A, if you compute the external product between A and U, then you obtain Ring-LW ciphertext, which is decryptable by S, and it returns, it is approximately equal to A times S prime. So it is something like multiplying S prime to A securely, and the result is a Ring-LW ciphertext encrypted by S. So this key switching technique is used in linearization, for example, where S prime is equal to S square, and also used in homomorphic automorphism, where S prime is equal to phi of S, where phi is an automorphism you want to evaluate, like a rotation. So this is why we are interested in key switching. And also, this key switching is a dominating factor in like a running time of these homomorphic operations. Like for example, in homomorphic multiplication, about 85 to 90% of running time is for key switching. In the case of evaluation of a rotation, automorphism, just more than 95% of evaluation time is from this key switching. So we just need to improve this key switching part. All right. So this is what we currently doing in many libraries. So we have a, we have a input ciphertext X, and this is a key switching key U. So this A and U are both written in their RNS form. So A is written in A mod Q1 to A mod QL, and each UI is written as a tuple of U1 mod Q1 to U1 mod QL. So first we decompose A into this one, and we need to compute this one. But this product is a product between some element bi in the ring of integers R and another polynomial ui with this modulus q. So how can we compute this product of different polynomials in different space? So currently we are computing the RNS representation of bi modulo q. So basically we are converting bi from R to R mod q by computing its RNS representation. And this conversion is extremely expensive because you need to perform like entity operations for all different modulus Q1 to QL. So you need to compute UI modulo QJ for all pairs I and J. So that's why it requires this quadratically many entity operations. And also, and then perform the linear product over Q. This is relatively cheaper because the entity complexity is n log n, but the multiplication complexity is just a big O n. So the key switching, that's why key switching part is dominated by these entity operations. And that's why a lot of researches on hardware acceleration is focusing on the implementation of entity to reduce this complexity. All right, finally, I'm ready to explain our contribution. So, okay, so the goal is to compute this linear combination in a different way, more efficiently. And the main idea is that previously we brought BI to RQ and perform computation in R mod Q. But my idea is to perform the computation over R, ring of integers R, as much as possible. And this can be done by applying the gadget decomposition to UI, saying that, as I said, gadget decomposition is good at representing an arbitrary element as like a small coefficient linear combination of gadget bases. So, and this C, this target polynomial is a linear combination over this U1 to UL with a small coefficient B1 to BL. But the UIs are just arbitrarily polynomial. So if we represent this each UI using gadget decomposition, they can be written as a linear combination of a gadget basis GI with a small coefficient, say VI1 to VIL. So this is a decomposition of U. So that satisfies UI is equal to the summation of Vij times Gj, linear combination of Gj with a small coefficient. Then this linear combination, that what we eventually would like to compute, is actually equal to this value, where this is again linear combination of Gi with a small coefficients. And these small coefficients are written as a summation of Bi times Vij. So where Bi's are entries of a gadget decomposition of A, and Vij's are like entries of gadget decompositions of UI. And now these polynomials are elements of the ring of integers without modulus Q. So now this computation can be done between small polynomials with a very limited small precision. That's the main idea. Okay, some facts are listed here, that since UI are usually entries of some evaluation keys, so they are fixed. So we can pre-compute its gadget decomposition Vij and reuse it many times, like for linearization or automorphism or whatever. And this Cj refers to this coefficients of Gj. So Cj, now they are small elements of a ring of integers, and its upper bound is determined by gadget decomposition H, not Q. So it's just independent from the ciphertext modulus size. And finally, we don't have to really compute this linear combination, because what you're interested in is just RNS representation of C, finally. And since Cj is written as a summation of Cj times Gj, and the RNS representation of C is simply the tuple of C1 to CL. So if once you compute C1 to CL, then that's the RNS representation of C modulo Q. That's it. Okay, so here's a summary of a new external product. We have input A and pre-computed decomposition of UI. And we also pre-compute this DFT form of Vi, J over this ring of integers to minimize the complexity. So in this algorithm, we first compute this gadget decomposition, but now over R. So now it takes only L DFTs over R. And then this computation is has the same complexity, L square multiplication with a unit complexity B over N. And finally, you have this C of J in the DFT form. So you need to compute its inverse DFT and again entity to obtain its RNS representation, but still the complexity is linear with L. So overall, you can obtain this RNS representation of C modulo Q, and this expensive operation like a DFT or entity, they just requires linear complexity, big O L. That's the difference. And finally, I would like to remark that this is a purely algorithmic optimization. So you will obtain exactly the same ciphertext as the previous method. So there's no difference at all in terms of like a noise growth or other things. You just get exactly the same ciphertext. Okay, so there are some features that I haven't explained in my presentation. So you can definitely apply the spatial modulus technique to manage the noise growth. And in that case, key switching key is generated in a larger modulus PQ. And moreover, I just explained prime decomposition for simplicity, but you can use arbitrarily RNS-based Gaussian decomposition, where decomposition is defined by A modulo D1 to A modulo DK. D1 to DK is again a product of several word size primes. And you can use another decomposition over modulus PQ for this key switching. So you have one Gaussian modulus for A, Gaussian decomposition for A, and another Gaussian decomposition for U. And we definitely need a multi-precision integral polynomial arithmetic, but its precision upper bound depends on the bound of these decompositions, so independent from ciphertext modulus. So we use the Letigo library to implement our scheme, and when we set some parameters, we try to find some optimal parameters to minimize our complexity, and this is the result. When the ring dimension is 2 to the 15 or 2 to the 16, these are like maximal levels you can take. And when decomposition size R is a decomposition size, the number of primes in each decomposition digit. When this decomposition size is 1, 2, 3, or 1, 2, 3, 4, we achieved this vector of speed up compared to the previous best known method. So we achieved about 2 to 3 times faster than the previous method. So you can literally achieve almost the same speed up vector for homomorphic multiplication or homomorphic automorphism. And another interesting observation is that so these two bars represent profiling of this running time for previous method and our method for prime decomposition. So previously, entity was definitely dominating factor in homomorphic multiplication, but now it is not. So entity or DFT is no longer dominating factor of this homomorphic multiplication. So you just need to parallelize inner product or CRT conversion, which is very GPU friendly. So that's why I mentioned at the beginning of my talk that it will change some like research direction on hardware, because entity or DFT is no longer dominating factor in this homomorphic multiplication. And it is very well, it will have like lots of synergy with the hardware research, because this is a CPU result, but this part will be reduced a lot if we implement this algorithm over GPU or other hardwares. Okay, so this is my last slide, and thank you for listening.
Thank you, Yongsoo. We have time for a quick question. If you have questions, please line up at the microphone right in front. Introduce yourself.
Yes, Yongsoo, thank you very much for your super interesting talk.
Thank you.
And great idea. So you just have experimented from what you just presented. You're presenting like the technique, and after that you implemented it, and you're reporting benchmarks. But is there like a more formal way to try to optimize the technique? Choose the parameters, the size, the different sizes in the decomposition? Or
Oh, that's a great question. So I didn't explain in detail in my presentation, but actually I gave some guidelines on how to choose these parameters.
Okay. Interesting.
But that guideline may not be useful when we implement this algorithm over like a GPU or other hardware because they have a different cost model.
Okay.
So at least for like implementation over CPU, I provided some guideline. So, and there's a full table you can check.
Wonderful.
Thank you.
Thanks.
Very good. Other questions? If there are no more questions, please let's thank our speaker.
Thank you.